applies more generally to holography, and we built a lot of new holographic tools. And holography may even be thought as actually defining what is quantum gravity non-perturbatively. And through this route, we understood a lot about Schwarzschild ideas black holes and how to extend them via the gravity fluid correspondence and so on. So it has been a remarkable 20 years where we learned a lot of things. But of course, the attention of the community as a whole, and if we kind of go back not to 20 years, but 100 years, was not so much ADS gravity, was more vacuum Einstein gravity, which is the home of Minkowski physics. And in that context, there's a lot of things we already know. I mean, for instance, if you study quantum field theory, you start and you have an S matrix and in and out states. And then from there, we can start discussing quantum field theory on curved backgrounds, and then discuss semi-classical quantum gravity, and it leads to Hawking radiation and all the puzzles associated with black holes and so on. And more recently, we understood that vacuum Einstein has a very large asymptotic symmetry group, the BMS group, which may play an important role. And also Einstein gravity, I mean, Minkowski space is the home of perturbative string theory. That's the only case where you really understand the UV of the UV structure of perturbative quantum gravity. And also, since this topic has been around for a while, there are lots of solution generating techniques and so on. So this is also a topic which we really understand a lot of things. So the one question I'd like to ask is, if you put them together, you can see we understand a lot of things here and a lot of things there, but there are a lot of things that are not overlapping. For instance, on this side, we don't really understand holography pretty much at all, even though the original arguments for holography based on black holes do not depend on asymptotics. So it should have been pretty much the same level of understanding, but it is not. We do not understand, for instance, how to count the microstates of black holes. We also don't understand quantum gravity non-perturbatively. And if we go to the under de Sitter side, there are also some things from here we don't have over there. Like here, as I was discussing earlier, we have the BMS group. Is there something analogous? Maybe not. So, and here we have powerful solution generating techniques, but these typically fail when you go to ADS. Over here, we have in and out states. This do not exist over there. So even though they're both gravitational theories, and we know a lot of them, there are lots of things which are different between the two. So this work is what it's trying to do is try to build a bridge between the two that's going to connect vacuum Einstein to ADS with the hope of transporting things we know here over there and vice versa. So if there is one thing that I would like to get from this talk is that, okay, this type of bridge, we built it to some extent. We haven't used it yet to transport things except in a rudimentary fashion. And what I would like to convey today is I would like to describe this, what this bridge is. And I would like to give you some flavor of what we have already done with this. Okay, so next is to explain what is the Ads Ricci-flat correspondence. Any questions on this general framework? Okay, so what is it? Okay, so here it is how we came about it. So you start with ADS gravity, and we're reducing ADS gravity on a torus of specific dimension. So now one can show that this system admits a consistent truncation to just a scalar field and a metric. And once you reduce, you get an effective description of these degrees of freedom, the metric and the scalar, which is described by an action of this form. We have a coefficient alpha that depends on the dimension of the torus, and we have a coefficient beta, which is essentially the cosmological constant. Okay, so if you want to study ADS on a torus, you can equivalently study the theory over here, and then can uplift up there. Now it turns out that if you start with vacuum Einstein, but now you reduce on a sphere, where now you have the effective degrees of freedom is again a scalar and a metric, and this reduction gives an action of exactly the same form, as it turns out, where now this coefficient alpha is given by this expression, so it depends on the dimension of the sphere, and this coefficient beta is related to the curvature of the sphere. Now, if one looks at these formulas, it's easy to see that one can go from one case to the other by taking d to equals to minus n. So these are going to relate these two, and that's the relation between these two is then is automatically implied by these two. So in this formula here, the dimension, either the d or the n, enter analytically as a parameter in the equations of motion, and then the idea is one can analytically continue from the one to the other. So let's put this again a bit more in the formulas. So suppose you have a solution of ADS gravity in d+1 dimensions on a torus. And let me also say here that when I say on a torus, the global properties are not important. So what is important is that you have d minus p minus 1 translational isometries. So I'm going to discuss this as having a torus because that's useful for that reduction, but actually one can prove all the formulas I'm going to discuss here locally, so none of the global properties are important. This is going to become more important a bit later. So suppose that you have such a solution, then from here you extract the metric from here and the scalar field. Then in these formulas you substitute, so there's going to be some expression from g and phi. You substitute for d minus n in both of them, and then you put them here. And now this automatically satisfies this metric is automatically Ricci-flat. And of course you can go the other way around. If you start from such metric, you can start from ADS metric, from Ricci-flat metric, you can go back to an ADS metric. So let me give you a few remarks. First of all, in order to do that, you need to have a family of solutions, which on the ADS side is given by the space-time dimension. So you need to have an ADS solution that exists for any dimension d. And you need to have a family of Ricci-flat solutions, where again the one parameter family is parameterized by the dimension of the sphere, this number n. Secondly, so when we do the analytic continuation, you should not think we do the analytic continuation after we reduce to the p+2 dimensional theory. So d and n are not anymore dimensions, they're just parameters of the theory. And clearly the solutions of this theory do not depend on what is the precise values of alpha and beta, except when you go to very extreme cases. So in general, if you have a solution of that theory, you can continue the parameter to some other value. And that's an example of what we call generalized dimensional reduction, which was developed in these papers. And the idea is precisely what I just described. So you do a standard dimensional reduction, keeping free the dimension of the compactification manifold, and then you analytically continue in that parameter. And so this map from ADS to Ricci-flat essentially trades the two curvatures, the curvature of ADS with the curvature of the sphere. And this is one example. We can actually already, in our paper, we discuss a large number of extensions, and one specific one was developed shortly afterwards in this paper. Oh, you now, instead of having ADS Ricci-flat, you have an ADS DS correspondence of the same type. So the punchline of that is that the resulting Ricci-flat class of solutions now inherits some holographic structure and some hidden conformal symmetry from that of the locally ADS solution. And in the following, I'm trying to exhibit some of that. Okay, so now next I'm going to discuss some simple cases. So any questions on it's all classical, it's all filter questions. So eventually, so here I envision kind of doing holography at a regime where gravity is valid. So then from that perspective, I'm just analyzing filter questions. But also, you know, if I want to go, you know, further and use it at the quantum level, and at the end of the day, it boils down to doing, in a sense, quantum mechanics based on that action. So one could envision extending it also at the quantum level. But at this point, we're just doing it at the classical level, classical filter questions, and then the quantum properties come via holography. Yeah, so for matter, for special types of matter, I will have some comments later on. The whole thing goes through. If you add generic matter, it's not clear whether these maps are going to continue. There are examples with. I will have a comment later. Okay, so let's first see simple examples. So first of all, it might look a bit contrived. You take the dimension, you take it to minus the dimension. Both D and N are meant to be positive. It may not be true, but not interesting. So let's see how it acts on simple situations. So first of all, it takes ADS and maps it to Minkowski. It takes planar ADS black holes and maps them to Schwarzer black holes. So it has a kind of very canonical action. And if you start with planar ADS and you extend them to a kind of a fluid gravity by adding gradients, it takes the whole kind of fluid gravity metrics and continues them to general black folds. And this works order by order, so it kind of every order works, maps properly each order to each other. And one of the early applications that we did is to try to understand kind of the Gregory-Laflamme instability. And this is kind of the Gregory-Laflamme instability in two lines. If you have conformal fluids, then you know the equation of state is given by this simple relation where E is the density, energy density, P is the pressure. Now, if I apply the ADS Ricci-flat map, I have to take T to minus N. So then the corresponding Ricci-flat solution is now given by that expression, and then from here you can compute the speed of sound, and you see the square is negative, therefore the speed of sound is imaginary. There is a sound instability, and that's precisely the Gregory-Laflamme instability. So even if you didn't know about it, if we knew this map, then we'd immediately conclude there must exist the Gregory-Laflamme instability. But actually, you can go a lot further. And here I'm summarizing things. There are some things we did and some things that done later in Roberto Eberand's program of 1 over the expansion, where this is the space-time dimension. So if you do an 1 over the expansion, one can compute at closed form the quasi-normal modes of the original ADS black holes, and then you can use ADS Ricci-flat to map this across to the Ricci-flat side, and this gives precisely the frequencies of the unstable Gregory-Laflamme frequencies. So that already, I think it's a nice application. Okay, so so next, so I said if you have ADS, this maps to Minkowski. So now let's try to do things we know how to do in holography. Let's put an excitation on top of ADS. So we put a normalizable mode in the bulk. So this means we turn on a holographic energy momentum tensor on the boundary. So now if you apply the map, so this map, this is system into a brain, which is located at the center of the space. And then this brain now sources Einstein equations, and the energy momentum tensor on the brain is precisely the energy momentum tensor of the holographic energy momentum tensor. And there is also a similar picture in ADS correspondence. So that starts to give a hint of what happens now with holography. So what do we do when we compute holographically correlation functions? We use directly bounded conditions to turn on a source, then we compute the response of the system to that source, and then to linear order, the response it gives, for instance, the 2-point functions. To quadratic order, it's going to give 3-point functions, and so on. So now if I translate that to the Ricci-flat side, then the Dirichlet problem on the boundary of ADS becomes a Dirichlet problem along the brain. And then the response of the system to this localized energy on the p brain gives the linearized gravitational field, which is precisely the 2-point function. And that works exactly also in terms of formulas. So from here, we start to see a coherent picture of how the perturbations on the Ricci-flat side are related to correlators of a theory in one-dimensional S. Okay, so let me summarize. I mean, this is in a sense what was already been done before. Let's summarize the status. So again, the NDH Ricci-flat maps asymptotically locally ADS solutions on a torus to Ricci-flat space-times, and this gives us a handle of how to start building holography. But the map, the way I described it so far, presumed this translational isometries on the ADS side, and then the rotational, the SON plus 1 isometries on the sphere side. So while this captures the dynamics properly on the extended directions along the brain, the transverse sphere is frozen, and this map in its form is not as useful if you want, for instance, to understand holographically perturbations of Schwarzschild black hole, because if the only things you can do is spherically symmetric just by Birkhoff's theorem, there's nothing to explain. So if one wants to extend the utility of this correspondence, one has to find a way to unfreeze the toroidal directions and the spherical directions. Yes?
If in the ADS side, instead of using a torus, you take a sphere, for example, you will get a similar looking action that you will change the curvature of the ADS part.
Yeah, so we did it for generic. I forget what it maps on the other side, but we did the reductions for generic Einstein manifolds.
I suspect, well, the reason I'm asking is that the torus has all these non-trivial cycles, but the sphere is more similar to what you have on the other side.
Yes, yeah. But sphere with sphere, we cannot map. You always have to, in a sense, you have to trade curvatures.
No, I understand.
Yes, yes.
But I suspect that maybe if we have a sphere instead of tori, maybe instead of getting these brains.
I'm gonna. So there may be other ways beyond of what I'm gonna say today. There may be other ways to kind of get rid of, let's say, the sphere on the Minkowski side. But we certainly have one way to go about it. Yes.
The reason I'm asking is because in this ADS and DS holography story, this is a bit how it works, right?
I see.
Formally related, and they have to do with putting ADS with some sphere, and then you can.
I see. So there may be relations. Yes. Yeah. I mean, here, of course, we're not doing any conformal transformations. In a sense, they happen. I'm relating metrics automatically, right? Not up to conformal transformations. Yeah. Yes.
Do an uplift, you add a matter that's conformally coupled, and when you reduce it, you get massive modes, and then you can see why the field symmetry arises. It's a way of tracking the field symmetry.
Yes, yeah. Yes, and then extensions, since Alejandro asked about extensions. Some extensions have been done, but usually this is done by reducing once more and then keeping the gauge fields, and then you can move. There are some examples where you can add matter, but in all of these examples, the sphere remained frozen. And if you want to attack, in a sense, the more interesting problem, you need to be able to unfreeze the sphere. So the new part of the work is about unfreezing these internal modes. So we want to be able to at least start fluctuating the torus or the sphere, and want to understand if we fluctuate the torus, what happens. Is there any sense under which this map continues to halt? Okay. Now, of course, if this is to halt generally, it only has to halt at the linearized level. So first I'm going to discuss how to do that at the linearized level, and we also have some results which are beyond the linear level. Now to do that, one has to understand in detail linearized fluctuations around ADS with a torus or Minkowski with a sphere. So the first step was to understand the Kaluza-Klein reduction. So here, when I had this map, here we only kept phi and the metric, but now if you want to unfreeze the other parts, you cannot just keep those, you need to keep all Kaluza-Klein modes. So a priori it looks like an impossible task. Why would fluctuations around the torus have anything to do with fluctuations around the sphere? So it looked like a kind of long shot with no chance of success. But nevertheless, you can say, okay, let's see what's going on. So we did this computation. This is actually not a trivial computation, and here I'm only going to sketch the results. But I think it's interesting of its own because there are not that many computations in the literature where the complete Kaluza-Klein reduction has been done for random modes. So now, okay, our task was to find the Kaluza-Klein reduction and then compare the modes and see are they the same or not. Okay, so here in formulas the problem we solve. So we start with Minkowski. So Minkowski I write as, so I split one part and I write it in polar coordinates. And then the sphere I had in my reduction is the sphere in polar coordinates. So I know that on this background I can do ADS Ricci-flat. But now what I want to do is I want to add an additional perturbation that now depends on all coordinates, not just these ones, but also the coordinates on the sphere. So now on general grounds, I can decompose this perturbation in harmonics of the sphere, and this is the general decomposition, where these guys, the blue guys here, are just spherical harmonics. And then the coefficients are infinite hours of Kaluza-Klein modes that you have in your theory. And if you really want to do this, there are issues about for choosing your variables correctly. You have to find the right gauge invariant variables and so on. So we've done all of that. This is going to be in the paper. And then you get equations for all of these scalars, vectors, and tensors. And then, so these are linear equations, diagonalize these equations, and find the solutions. Okay, so this is one exercise. And then the second exercise is to do the same, but now ADS on a torus. So now we can convectify some of the boundary directions of ADS. And we add general perturbation that depends on all of these coordinates. And the procedure is similar. Again, you expand in harmonics on the torus, you extract the coefficients, diagonalize the system, and do all of that. And then you have two sets of equations and say, are they the same or are they different? Okay, so I'm not going to give you, if I were to give you all the results, so it's going to fit a few slides. I'm just going to tell you the building blocks. So on ADS, all of these modes depend on Bessel functions in this specific combinations with the index is related to the space-time dimension in these three combinations. And on the Minkowski side, also depend on Bessels in a very similar fashion. And now if you compare them one by one, then you can see if you take the large limit and the large delimit. So when I take the large limit, this means n over 2 is bigger than L. So this becomes j of n over 2. And over here, this j, so this factors 1 and 2 are irrelevant in this larger limit. Then we can show that all modes, one by one, exactly match. So even though this looks like an impossible task, nevertheless, in this large n limit, there is a one-to-one correspondence between the modes. So physically, you take the number of space-time dimensions to be very large. So we already know, for instance, that gravity in a large D limit simplifies, and that might be, in a sense, another of the same phenomenon. I don't have a better explanation. It's once you see all the modes, and this all infinite hours of modes exactly match in that limit. So that's okay. That's that's great. So at least in that limit, perturbatively, one can completely unfreeze either the torus or the sphere. So what about finite n? Okay, so the ADS Ricci-flat definitely works in this limit. Does it work for finite n? And the answer is yes, it works. The map is a little bit more complicated. And now I will try to sketch the idea. So let's start from the Minkowski side, where we have a sphere. So instead of starting from the beginning with general perturbations, so let's first start by, we do not unfreeze completely, entirely all the sphere, but we unfreeze part of it. So the sphere can be written as a vibration of two spheres, and then we can take perturbations which are invariant under this Sn+1 sphere. So we can do that. We can first partially unfreeze the sphere and then understand how to further unfreeze it. But now, once we have a sphere into our system, we can apply the ADS Ricci-flat map the way I described it earlier and map it to a torus. So that gives us an access to these modes. So let's see how this works in practice. So first let me take these pictures into formulas. So again, I start with Minkowski, where I have written this part in polar coordinates. And now I want to write this sphere as a vibration of two spheres over an angle. And now the idea is that now when I'm going to consider perturbations, I'm going to allow them to depend on this part, but not on that one. Now, since nothing depends on this, I can now use the ADS Ricci-flat to rewrite it as a torus. And then after the change of variables that depend on this psi and r, I can bring this back here. And now I got my torus. Now it depends on this torus that came from the ADS Ricci-flat part. And then there is an additional flat part that is related to the original psi. So essentially, the dependence on psi becomes dependence on psi. Okay. So let's see this, and one can also do it the other way around. So here we want from Ricci-flat to ADS. We can also go from ADS to Minkowski. And this is an example where the things work at a nonlinear level, not just a linearized level. So let's start with an exact solution of Einstein equations with negative cosmological constant, a traveling wave. So a traveling wave is specified by this harmonic function that depends on one of the light-cone coordinates, depends on the radial or the ADS radial coordinate. And also, in general, it depends on this transverse coordinates. So, so these transverse coordinates, I can now write them as, split them as p plus 1, which are part of my remaining space-time, and part which are toroidal. And now I can do the Ricci-flat either on the original set here, and if I do that, then I get a traveling wave on a Ricci-flat traveling wave, or I can do it in a smaller torus, which is now going to give independence on this additional coordinate psi. So when I do that, I end up again with a traveling wave. So let's put them again. So let me summarize what I've done. So so I have my traveling wave in ADS, then applying the ADS Ricci-flat on this part, I got a traveling wave on Minkowski. But I'm really interested in viewing this part as part of an original sphere, so I can rewrite this as an n+1 sphere, and then get this form of the traveling wave. And now this perturbation expanding in harmonics of n+1 becomes this infinite superposition. So the punchline of this is we can map a single ADS mode to an infinite superposition of Minkowski modes. So if you do not take the large n or the large d limit, what happens is you map a simple mode to infinite superpositions of other modes. So here, I'm sure this went very quickly. But this mechanism works completely generally. So you can take any mode in ADS and then use this same trick. And then the result is that you can map it across, but then the resulting perturbation is a superposition of modes. So this now gives us a general method that would allow us to transport the map, the ADS holographic dictionary, now to asymptotically flat spacetimes. And in principle, same thing, you can do the same thing also for Schwarzschild black holes. Now, if you do this, you can still complain that the only thing that I managed to do is I managed to describe perturbations which still have a symmetry. They were still SON+2 symmetric. So can I relax that restriction? Well, you can relax that restriction too. So what it requires is that after you do the map, you take the limit n goes to -1, where this sphere here now disappears. And in that limit, what was originally a sphere, we get half of the sphere, and this describes the general perturbations of half of Minkowski. Okay, so now this now gives us, let's say, the more general formulation. Suppose you're interested in properties of Ricci-flat spacetimes in p+2 dimensions, not necessarily perturbatively, non-perturbatively. So the general method to do this is to first uplift this to a Ricci-flat solution in n plus p plus 3 dimensions, such that if I start from here and set n to equals -1, I go down there. Now, this introduces the one-parameter family of solutions that we're interested in, and then we can apply the ADS Ricci-flat map to map it to ADS p+1 gravity. So then another properties of Ricci-flat manifolds in p+2 dimensions follow from those of ADS gravity in d+1 upon the limit n goes to -1. And you can do also the same on the other side. Suppose you're interested in properties of ADS p+2 gravity. For instance, you want to know general linear perturbation. Is this general linear perturbation related in any way to some linear perturbation of Ricci-flat manifolds in different dimensions? And the answer is yes. You first lift this ADS P plus 2 gravity to ADS T plus 1 gravity on a torus. Then you map it across, and then you take the limit D equals to P plus 1. So this links directly this perturbation. So you can again see this explicit with formulas. This might look pictures, but there are concrete formulas behind it. And also there is one example where actually this side here has been done already in complete generality. So suppose we have black pea brains and fluid perturbations around it using fluid gravity correspondence. Now if I take the limit and go to -1, this removes this sphere, and this becomes Rindler space in P plus 2 dimensions. So now we can see from here that Rindler in P plus 2 can be obtained from black pea brains with a sphere. And then for those, we can apply the map to map them to ADS black pea brains in fluid gravity correspondence. And then we can apply this limit to the results from here. And that gives exactly the Rindler fluid metric to second order in the derivative expansion and all the corresponding transfer coefficients which were computed in these papers. Actually, we spent more than a year computing those back in 2012, and we observed there was exactly the same number of transfer coefficients as second order ADS fluids. And not only that, but the coefficients were exactly the same. So why did it have to be the same? So this exactly explains why this Rindler fluid results were the ones that we got, because there is a direct link via the small general correspondence. Okay, so before I conclude, any questions? Okay, so let me summarize. So what we've seen is that perturbations of Minkowski spacetime can be mapped to perturbations of ADS, and this should allow us to exhibit many properties. For instance, the flat spacetimes should inherit some of the holographic properties of ADS. So what I discussed today is how to unfreeze the sphere and the torus, and we've seen that in the large D and N limit, individual modes are exactly mapped to each other. For finite D or N, single modes are mapped to superposition of modes. So, so now we, in a sense, completed at least the first version of that bridge. We know how to go from one to the other. So there are clearly a lot of things to explore and uncover. So the link implies that asymptotically flat spacetimes should have some underlying conformal structure just by transporting it via the map. Of course, we've seen in the past there are a lot of results about hidden conformal symmetry. May or may not be related to this. There were certainly hints that there are some hidden conformal invariants in many contexts. This gives a systematic way to explore such connections. We've seen some hints of how to build holography for each flat spacetimes via this map, but clearly there's a lot of more things to be done. We just scratched the surface. And even for more mundane things, once you have the map, you can now, if we know a lot of solution generating techniques in the Ricci-flat side, I can use the map to transport them to get new interesting solutions on ADS and many, many more. Thank you.